Yes, good afternoon, friends. Myself, Narendra Dhaigude. I am associated with Prerana since 2014, and particularly for BE trainings. I normally take the subject that is Book 3, Chapter 9, Book 3, Chapter 9 for DG sets. That is my core experience in HT motors, alternators, and basically rotating electric machines. I am having my own business and being basically in rotating electrical machines. So here we will start this training. It is basically his PowerPoint presentation is there. Wherever you are having any questions or doubt, you can we will discuss like that. There is no any problem because today the we are only four people are there. So interaction will be rather better. There is no doubt about it. So I share the screen for the PowerPoint. Okay, is it clearly visible?
No, sir, not yet.
Not yet. That one wrong. Share the screen. Yes, entire screen. Share. Okay, is
Yeah,
it visible now?
yeah, it's visible.
Yes. Okay, right. So this is on diesel and natural gas power generating systems. As per the book, the chapters are basic and basics of internal combustion engines, diesel and natural gas power generating systems, factors affecting performance, wastage recovery in diesel natural gas power generating system, performance assessment methodology, and energy saving measures. Wherever you feel that this information is um, inadequate, you can ask, or if you want to skip that particular topic, you can indicate that also. But anyway, I will cover the entire topic as such. When we say DG set, this is a general picture what we see about the DG set. Then the basic components or the as a system, there is engine inside, there is alternator, there is battery to start the engine, and there is control panel. This is acoustic canopy, acoustically enclosed canopy. So here it is shown this engine and alternator they are coupled together. There is no separate coupling. The alternator is directly mounted on the bell housing of the engine. So that's why it is called as a closed coupled DG set. Earlier, there used to be a separate coupling in between that was long coupled DG sets. Now, as a diesel engine is energy generating equipment, so I always look at the engine as a human, all human characteristics. Whatever inputs, outputs are there of the humans, the same all features are there in the diesel engine also. There is fuel pump, there are fuel filters is there, the bell housing, starters, everything. So what are the systems? This air filter that is to take the air intake, then exhaust manifold, whatever is the gas exhaust, it is there. Radiator is for the cooling, oil filter is there, and oil sump is there. This is a common sense everybody knows. This is a cut section of diesel engine. There is a piston. It moves in the cylinders. When we say this as a system, so engine, alternator, controls, radiator, base rail, anti-vibration mounts, coupling between alternator and prime mover, and acoustic canopy. These are the main components of a DG set. Now in the four-stroke diesel engine cycle, why we call it as a four-stroke? So there are four movements happening successively in any diesel engine. First is induction, second is compression, third is called as ignition, and fourth is exhaust. So that's why it is called as four stroke. And in this, the valves are controlled by camshaft. What are the functions of each one? So when induction stroke is there, the air is taken inside, that is called as induction. In the next, the air and fuel, it is compressed. In the third, the fuel is injected and it is ignited. So that's why it is ignition. And because of the ignition, there is expansion of the internal air and it pushes the piston downwards. So it is called as ignition or power stroke. And the fourth one is exhaust. So when it moves up, whatever are the exhaust gases are there, they are thrown out. So this is a general four-stroke cycle. These things we have already learned in our engineering. Now here, when there is a compression, the internal fuel gets heated up and the temperature goes up to 700 to 900 degrees centigrade because of the compression. The compression ratio is varying from 14 to 25, whatever is the volume. So that volume is compressed to such a pressure, and that's why the fuel gets ignited. Just a minute here. I don't see there is any animation in this happening. I don't know why. Just a second. Ah, yes. So whenever there are movements of the pistons, they rotate the crankshaft. Ultimately, the flywheel is rotated and it is coupled to the alternator. So here there is a camshaft and this is a crankshaft. This is for the power transmission and this is for the controlling of the valve. So this is arrangement of four-stroke diesel engine. Now in gas engines, what happens? Instead of diesel directly, the gas is injected in that and there is a spark plug. So whatever is the gas mixture is there, gas plus air mixture, after compression, it is ignited and this cycle continues. Again, the same thing, induction, compression, ignition, and exhaust. This is a total schematic of this spark plug engine. This is shown in animated. The air is taken inside. There is a spark and there is exhaust. So in short, fuel is burnt inside engine. So that's why it is internal combustion engine. Heat produces 700 to 900 degrees. Because of this, the cylinders get heated up. We need to cool it. The cooling water gets heated up and we have to extract the waste heat from these cylinders. Now there are two types of diesel engine. The smaller engines are normally air cooled and the larger engines are water cooled. In the air cooled, maintenance is low. They are not suitable for hot environment. But if the ambient temperature is increased, we don't have any control for cooling it. Also, it is not suitable for dusty environment because frequently we will need to clean the air filter. So they are suitable for small ratings. And of course, for the water cooled engines, advantages are many more. They require basically water pump and other parts, little more maintenance is involved. If required, cooling can be increased by adding coolers, etc. They are compact in size naturally. They are suitable inside the canopy also because radiator goes inside and must be in large ratings, compulsory. Now the basic interest is to learn, or our interest is to use the waste heat. So far as energy conservation is considered or energy balance is considered, our eye should be focused on whatever is the excess heat, excess energy is going. Now the total cycle is, this is a reciprocating engine. After burning the oil or the diesel, this exhaust gas is there, which is very hot. So we can extract heat from this. Also, the lubricating oil cooler is there, jacket water cooler, and charge air cooler. So these three equipments are there for cooling of the oil, etc. So again, there is excess heat, and this heat we can utilize by some another means. And the engine is coupled to generator. So generator gives electrical output. So the entire system is, there is input fuel and output in the form of electrical energy plus all these heat energies. Now, can you guess what is the percentage of excess heat in a diesel engine? It is almost 60% losses are there, and only 30 to 40% output is utilized for electric energy generation. So you can understand the gravity of heat extraction or excess heat utilization from a DG set. That is why DG set is not economical to use that way. So diesel engine as a schematic, again AC generator is there. So what are the other factors? For generator, controls are there. From load side, again control, the feedback is taken from the load side. For engine, there are many more accessories. There is foundation and fuel control system for diesel engine. Now, in general, what we consider everything, what is the input or what, this is called as a specific fuel consumption. So in earlier years, during 1970 or around that, the specific fuel consumption was 220 grams per kWh generated, because that time there was no other systems, whatever is the injection system was there, that was utilized. But further, what has happened, there is a turbocharger. A turbocharger is connected at the exhaust of the engine, and on this exhaust the heat energy is converted in rotational energy by a turbine. The turbine drives the compressor, and the compressed air is fed to the engine, and thereby the engine capacity is increased. Just like when we see the weightlifters, or even for our experience also, when we are lifting some heavy weight, we take a deep breath. So air intake is much more, it is a compressed air, we hold the breath and do heavy work. So same system happens here. The air is compressed, and this cold compressed air is fed to engine, and engine capacity is increased. So thereby it needs less fuel consumption per kWh, and it increases overall thermal efficiency of the engine. So nowadays we see that almost SFC is around 160 grams per kWh. Same thing, it is compressed air. Compressed air is used. Now we see the selection of DG set. For selection of DG set, there are multiple parameters, but basically DG set is selected on the basis of load, then the type of alternator, then whether it is a standby duty or continuous duty.
Sir,
Uh,
can you just elaborate that efficiency? You are saying that 40% and 60% is wastage.
yeah,
In
there is a chart. There is a total design chart of Mahindra engine. In next slides, the chart is there. So you will
Okay.
come to know all the classifications and segregation item wise, and how it comes to 40%.
Okay.
All those design features are given by the manufacturer itself. I will show.
Okay, sir. Okay. Yeah.
So while selecting what type of load, type of alternator, these parameters are there. So initially we have to understand how much is the power requirement, that is electrical power requirement. So here is it is a compressor. For compressor, motor is needed. For blower, motor is needed. This welding generator, lighting is there, pumps are there, some camera, etc. But everywhere there either there is a heating load, there are motor loads, that is maybe inductive, maybe resistive loads. So whatever is the electrical load, ultimately it is converted in kVA. Electrical load is converted in kVA, that is the base. So I say kVA means, you can say it is Indian rupees, INR, that is a unit. Because ultimately whatever is the expenses are done, they are done being in terms of rupees, whether we use credit card or GPay or whatever it is, but ultimately it is converted in rupees. So all the electrical loads are converted in kVA. Now, as a thumb rule, in general, whatever is the load, the DG set should have at least 10 to 20% capacity higher than the load side. This is again the common sense, because some another parameters are there. So prime mover has to be uh, have some capacity, a marginal capacity over and above that. The basic reason is, even though we are having some expenses, some 20% we keep it in inside pocket for the extra demand or sudden demands are there. 20% margin required for sometimes momentary overloads are there. Sometimes electromechanical stresses are there, and impurities of the fuel. We consider that this is the specific fuel calorific value of the diesel, but diesel may not be exactly pure and as specified. So impurities may also cause this problem. So that's why we keep a margin of 20% over the capacity. Now we come to the alternator part. Alternator is basically electrical equipment. It is a rotating magnetic field type instrument. By the engine shaft is driven, the field is rotated, and when the field is rotated with respect to some conductor, EMF is generated or voltage is generated in the winding, and this voltage is taken at the terminals. For this is a main stator. There is automatic voltage regulator which controls the field voltage, exciter field voltage. It controls the excitation, that is magnetic flux generated by the rotor is controlled by automatic voltage regulator. There are rotating diodes, and this is main field rotor. These are the general parts of alternator. As a principle, this is a universal principle that when a conductor is rotated in uniform magnetic field, EMF or or voltage is generated in the conductor. So this is rotating magnetic field, and there are three phase windings. So one after the another, the voltage is given to the fields, and that is why we say what is the phase sequence. So phase sequence is L1, L2, L3, L1, L2, L3. This is a phase sequence. In electrical terms, in wiring, in cabling, we say this is RYB, RYB, RYB. If it starts rotating in the reverse way, it will be L1, L3, L2. So that is RBY, RBY. And because of if the supply is reversed by mistake, the motors also start rotating in the reverse way because of this phase sequence. Here what we see is a graphical presentation of the alternating voltage. Now what are the selection considerations? Basically, the speed of the engine or speed of the alternator is decided. Normally, we select alter engines with a speed of 1500 because it is a four pole alternator. This is a general formula. We know speed in revolutions per minute is 120 multiplied by supply frequency. So in India, we use 50 hertz frequency, 50 hertz sequence. And this is number of magnetic poles as shown in the generator. So when there are four poles and 50 hertz standards, the speed is 1500. When the speed is 3000, it is a two pole alternator. So we will have to select engine for that alternator, either 15,000 rpm engine or 3000 rpm engine. And there are engines having rpm 1000, 750 or 600, like that. So in the tabular form, we can see poles of the alternator: 2 pole, 4 pole, 6 pole, 8 pole. It is a even number. And at 50 hertz supply, the speeds are 3000, 1500, etc. 60 hertz are being used in US, so their speed is naturally it will 20% higher than this. Now, on in the market, or in the market road, there are these small genset used in the shops. They are having higher RPM, and the large DG sets, they are having 1500 RPM. Now, specifically, if you see the difference, the 3000 RPM engines are compact because their RPM is higher. As the RPM reduces, the size of the diesel engine goes up. So here we have to see for which alternator, which engine is suitable. So selection criteria is on the basis of the speed. In the next slide, you see the RPM is 1000, and what is the size of the engine. So here again the RPM is reduced, and these type of engines are ranging to 4 megawatt to 12 megawatt. So as the speed reduces, the size is increased. The advantage is, as the RPM is low, the frictional losses are very low, the centrifugal forces are less. So that is why the life of these engines are very much higher. Comparatively, maintenance is less because of the lower RPMs. But the initial cost is very high. So this is one of the uh, problem with that. So this is Skoda genset. This is 10 megawatt, and this is 375 RPM. So 10 megawatt, 375 RPM, and 10 megawatt, 1500 engines. Of course, in the larger one, uh, higher speed engines are not there, but as a comparison, we can see here. So this is a comparison of slow speed and high speed engines. These are slow speed, and this is high speed engine. That is 1500. So just we have said about it as a comparison: slow speed engine versus high speed engine. Slow speed engine is something like this: the speed is very less, but the size is bigger, and comparatively the power is much higher. And here the speed is very high. So that is why the wear and tear is low in slow speed. The weight is very high. The space required is very high. But here we can use a continuous type of duty, and diesel engines or rather 1500, they are of intermittent disease. Boxer cannot fight for a longer time, maybe for half an hour round is there, but the larger engines are used for continuous use, so that's why for captive power plant slow speed engines are ideal. Here the period between overalls is 8000 hours, here it is 3000 less. Operating cost is very less here, in this case it is very high. Initial cost is high, and the basic difference in fuel is high speed use diesel, and in low speed it is LDO. This is a single bearing alternator directly coupled to engine. These are long coupled, so there is coupling in between these two. This we have seen. Now this is captive power plant. Multiple diesel engines are installed. Now for different types of generating stations. Here the combined gas turbine and steam turbine. The another one is conventional steam plant, and the third one is the diesel engine power plants. There are the parameters: this thermal efficiency, initial investment, space requirement, construction time, project auxiliary power, plant load factor, and startup time from code. This table is already given in the book, so I will not repeat it by point to point. But here, what we have to focus on this: the diesel engine power plants, their thermal efficiency is 43 to 45%, whereas in steam the losses are very high and efficiency is less. Here the initial investment is also less for diesel engines. Space requirement is comparatively less than the other two. Construction time, it is very less, because it is just a part of assembling an alternator, engine, base frame, and control panels. So construction time is very less. Project period is very less. Then plant load factor is, it is, we can get better load factor so far as utilities considered, and startup time is also less. So these are the advantages of diesel engine over the other one. And nowadays space is a constraint, and the cost of the space is very high, so that's why diesel engine plant consumes less area, so that's why they are economical even in that aspect also. So these are the main factors: low installation cost, higher efficiencies, etc. Now there is a capacity combination. There are one, two, three, four, five, or whatever it is. Depending on the demand, we can select the capacities of the gensets. Say, we'll take a small example. Say, in our office, there are some fan, there is a pump, lighting, building, compressor, etc. And suppose the kVAs are 40, 50, etc. So totally it is 285 kVA load is there in our factory. But if only fans are running in the process, or fans and pumps are there, furnace is not being operated. So particularly for that period, we need not run the 285 kVA DG set or 300 kVA DG set. So how to select the capacities? So we have got multiple choices. Either go for 200 kVA, or 100 plus 100 kVA, or 50 into 3, or 25 into 3 plus these combinations. So depending on our priorities of the running of the equipment, which is dependent upon the process. Now, though the electrical engineer cannot define this sequence is defined by the process engineers. Electrical engineer has to cope up demand as per the requirement. तो इसमें कितना चालू करना है, कितना बंद करना है, हाउ मेनी विल बी रनिंग एट अ टाइम, which is critical, and as per the priorities, the capacity combination is selected. Okay. Now this is a general power flow of DG. Here there is a fuel input, which is a chemical energy. Calorific diesel is the input. There is heat loss. This is active power. So this active power is the input kilowatt to the alternator. Then there are some losses in the alternator, and whatever is the remain, that is the output in terms of kVA. So we give chemical input, it is converted in mechanical energy, and this mechanical energy is converted in electrical energy. So this is a general energy flow or the power flow. Now look here, the fuel input, say it is 100%. So out of this 30% heat energy is gone to the exhaust, and 25% is lost in cooling. 5 to 10% is lost in radiation, and whatever is the remain, that remain goes for electrical energy or to the alternator. Now this part is alternator. Now in alternator there are iron losses, that is the stator copper losses, stator loss. Then this is copper losses, that is happening in windings, rotor copper loss, exciter stator, frictional losses, windage, stray losses, and whatever remained is only 25 to 30% of all the 100% fuel inputs. So ultimately, we see as a thumb rule that total efficiency of the DG set is around 35 to 40%. But we have to look here. Whatever is the exhaust, cooling, and radiation, waste heat is there. We will see the factors in the next slides. Engine thermal efficiency. This thermal efficiency I will take it in the next day. Now, many a times we come to notice that how the energy flow is there. Suppose this is a general, a common pump set. We say pumप कितना का है, एक 10 एचपी का है. 10 एचपी मतलब से 10 से 7.5 किलोवाट. Now the output of the pump is 7.7 kilowatt. That is mechanical output of the water, pressure into discharge into density, etc. But the pump is having efficiency of 70%. So its pump input needed is 7.7 divided by zero point 0.7. So pump input is 11 kilowatt. When pump input is there, motor output is equal to pump input. The motor efficiency is 90%. So motor has to have input of 12.22 because output is 11 kilowatt divided by zero point 0.9. So this is input is 12.22. Now in between there is a starter. Starter doesn't consume any energy. After that, this energy, this 12.22 kilowatt must be the input to motor, which is equal to output of the alternator in electrical. So 12.12 kilowatt at a zero point 0.8 power factor is equivalent to 15.27 kVA. तो इतना तो जनरेटर कैपेसिटी होना है यहाँ पे. Now mechanical energy 12.22 kilowatt power generated, again 90% efficiency of the alternator. So what is the mechanical input required is 13.6 kilowatt should be the input. That means output of the engine is 13.6 kilowatt. So if we consider right from diesel engine to the entire output to the utilization or to the consumer. This is 13.6 kilowatt, this is 7.7 kilowatt. So overall the efficiency is around 50% only. So running any electrical equipment or the plant load on a DG set is economically not feasible, or it is not economical, so to say. That is why the diesel engine sets are normally used for standby capacity. When grid power is not there, use these DG sets. तो इसमें तो पहला सवाल आता है कि अरे यार कितना देती है. Whenever we purchase any vehicle, whether it is a scooter or a car or electric vehicle, whatever it is, कितना देती है, what is the percentage, what is the specific fuel consumption. So by definition, the SFC means it is liters per hour, that is engine HP multiplied by SFC grams per HP per hour. 830 grams per liter is the density of the diesel. It varies. It may be from 850 grams to 830 grams or like that. So engine HP is at 100%. So normally the SFC is mentioned at 100% load. So SFC is different at different loading. The meaning is that a specific fuel consumption, if I am having a 100% workload, that is daily I am going for a duty for 8 hours, 9 to 5:30 I am having a duty, and I do a breakfast or I do have a lunch of 4 chapatis. But suppose there is a holiday, on Sunday there is no work. But if there is no work, that does not mean that I cannot eat anything. So even at a 25% load, the input is much higher. So the SFC values differ at different loading. So that thing has to be kept in mind. At higher temperature, the grams will increase, of course. This we have seen earlier. Okay, here there is just a schematic. So how the turbo is used. So whatever is the hot air is coming out from engine, turbine is driven. The turbine compresses the atmospheric air. It compresses. It goes to the intercooler. After that, cold air is given to the engine. Now the question is kitna deti hai? Here is a comparison. This is a typical format of DG monitoring. You see, uh,
Sir.
SFC is average load at 89. This chart is there in the book. So,
Narendra, sir,
huh?
I'm sorry, but I'm not getting your shared screen.
Okay, I will just.
Anybody's, or is this problem with me?
नहीं, just a minute. मी पुन्हा एकदा
No, whereas I must not able to see the screen.
आधी येतोय?
Ah, yes, sir.
Yes, sir. Yes, sir. Yes, sir.
I think there was some dip in the internet connection. There
Oh,
was dip because I think for some time the recording also was stopped. Maybe because of that. But okay,
okay.
now it is visible. For how much time it was not seen?
3-4 minutes. I think so.
4 minutes. Okay, okay. Then I will just go back to. I will just go back.
Only problem, sir. Problem only. At the problem.
Uh,
This,
we
this,
have seen this one.
yeah, yeah. This one we have seen. This one we have seen.
This one we have seen. This one.
Yes, in this
Yes,
only,
sir.
sir.
This,
Okay,
yes.
this one, this one may have seen. Okay, okay, this probably we missed this one. Okay, anyway, this is just an animation. Um, so it is just a typical format of DGSET monitoring at average load at specific fuel consumption, specific oil consumption. It is a comparison is given so for various load capacities, nothing else. Here you can see for LDO and for the higher capacities, the SFC is less. You can see in this chart. SFC is less for larger machines. As the engine capacity is reduced, the SFC is increased. But by and large, almost they are similar. For LDO, they are better. Now we see the uh, optimization. Say conservation or energy saving, etc. These the concepts are okay, but ultimately we have to consider the optimization. I share you one thing. In this Pune Pimpri Chinchwad Municipal Corporation, they had one drive of this energy audit and energy conservation, etc. So I had seen the report that copies with me that this consultant he has done the survey and he said that we have to save the energy. So what we have to do, so whatever are the street lights, normally the street lights are they are placed at a distance of 40 meters between each other. So instead of 40 we keep the distance 80 meters in between, so thereby we can save 50% energy. So that was the advice given by the particular consultant. So reducing demand or that is not the solution. We have to meet the demand whatever is demanded by the process, that is necessary. And that is why I always say that energy saving is a fishy word. I always say optimization must be looked after. It is not just saving. नहीं तो क्या होता है, ये सेविंग करने के बजाय ना पूरा अपना जो टारगेट है वो तो खत्म हो नहीं पाता है. Now, for the continuous operation and standby operation, now there is a specific uh, difference in between. Continuous operation is where supply from electricity board is not available at all. That is the first thing. Requirement in addition to electric EB supply, whatever is the board is there, if it is not sufficient. And third is the cogeneration. So in this case, only continuous operation is advisable or it is feasible. Standby operation is only in case of failure of electricity board supply and to meet the emergency for a short time load. Now, by specifications, short time load means only 1 to 2 hours at a time, not more than 2 hours. That is the first condition given in the specifications. Now, selection and installation factors to decide the correct rating of the genset. Uh, just a minute, I will see whether uh, this is being recorded. Just a hold on for a minute. Yes. Sure. Okay, is it visible now?
Yes, sir,
Ah,
visible.
yes, yes.
Yes,
I
yes.
just confirm whether it is being recorded. Otherwise, recording बंद हो जाता तो क्लाउड पे नहीं मिलेगा. Okay, yes. Uh, to decide the correct rating of the genset, if genset is too large, then optimization of the rating is necessary. So in this set is always used at partial load, unnecessary capital expenses हो जाते हैं. Okay, these are general information. I will not stress more on this. Then we have to see what is the total connected load, maximum demand, average load, demand factor, load factor, diversity factor. But out of all these, we will concentrate on the connected load, the load factor, and the diversity factor. These are the main three things. What are the environmental site conditions? Whether ambient temperature, then the altitude, whether the derating is applicable for the engine and alternator, etc. That we have to see. Then the next is leading or lagging power factor of the load. So that is a characteristic of the load. The power factor is not decided by the alternator, but it is a characteristic of the load itself. Next one is imbalance in the load of the individual phases. Whether there are any harmonics in the load side, that is also one of the major factor. Then we have to see the block load or single step load and voltage dip and load characteristics. So these are the other factors to be considered while looking at DG set. So here, the first thing we see, what is a demand factor? So demand factor is the maximum demand divided by connected load. There may be 100 equipment connected, but all of them are not working simultaneously. So we find out the maximum demand. The simplest way to find out the demand is that total kWh supplied in a day divided by 24 hours, that is, we call it as an average load demand. For 2 3 days, we conduct this exercise and we come to know what is the normal requirement. But this requirement may be different in summer season, may be different in winter season, depending on the type of the establishment. If it is a mall, naturally the demand is higher during festivals. At the other, the demand will be less. So as a simple graphical representation, we can see here total connected load, peak demand, average load demand factors. So in morning and after, or the during daytime and night time, the demands may be different. Say for example, the in the in early in the morning, 9 o'clock, the demand is this. Then the demand is increasing in steps wise, and suddenly at the evening there is during the change of the shift there is no demand. Then in the second or third shift the demand has gone up. Sometimes there was a peak demand also, and this is a load pattern. By this we come to know what is a total connected load. This is average load, and somewhere our rating will be in between these two, average and total demand or peak demand. We have to take a call, we have to calculate it, we have to see the data, we have to see the logbook, and depending upon that, we have to select the rating of the TG set. Now this is a diversity factor. Diversity factor is, say there are 6 loads connected, but we assume that these are equal, and at a time only 3 are working, either L2, L4, L5, or maybe L1, L3, L6, like that. So here the probability of working load at any time is only 3 at a time, and therefore the diversity factor is 50%. This is the first factor we consider, that if all the equipment are not working, first part. Then the next factor is a load factor. So what is load factor? See, this pump is, say, 10 HP, but when it is operating at 10 HP, when the water is pumped at a 10th floor, say at a height of say 20 meters, but if the same pump is used and the water tank is at 15th floor, naturally it will not consume 10 HP. It will be less. It will be some 7.5 HP. But if the height is less, again the output will be less. So the load on the motor is less, and that is called as a load factor. So this is the second part. All the motors are never running at 100% load. Normally we keep some 10% margin. So by and large, they are between 80% to 90%. So we consider load factor at 0.8 to zero point 0.9, which is economical. So here there is a calculation of load factor. See all these loads. Say initially all loads are there, but only L1, L3, L6 are running. These are the nameplate values of these motors. Say 10 kilowatt, 20 kilowatt, and here it is say 50 kilowatt. But this motor is running at 7 kW. This is running at 15 kW. This is at 50 kW. So all put together, it is 106 kW actual load is there, whereas the rated will be total 132. So here the load factor is 106 divided by 132. So load factor is zero point 0.7. So the first was diversity factor, second was load factor. If we multiply these two things, we come to selection of the genset. We see here step by step one simple example. The connected load is 132 kVA. Now the diversity factor is 50%. 132 into zero point 0.5 is 66 kVA. Estimate from the loading cycle chart. Now these 66 kVA are running at 70% load. That is load factor is 70%. So therefore, the actual demand comes to 46.2 kVA. So estimate from the design. Now we have to consider other factors. What is the overload margin, which is somewhere around 20%. So 46.2, 20% more 55 kVA. But this generator is working at a 1500 mean sea level, up to 1000 meters mean sea level. No duration is required, because at a sea level or up to 1000 meters level, air is sufficient for combustion of the fuel in the engine. As the altitude is increased, the duration is applied. So as per the chart, I will show you the chart. As per the chart, duration at 1500 0.855. So 55 kVA divided by 0.855 comes to 64 kVA. Again, the duration factor for temperature. All these gensets are designed to operate maximum up to 40 degrees ambient. Now here, practically the ambient temperature is 46 degrees, which is higher. So duration factor is 0.93 for 46 degrees. So therefore the requirement goes to 69 kVA. Now which is the nearest higher rating is 75. If no duration factor is there, then 55 kVA, nearest set will be 63 kVA. Because of the durations, we have to select 75 kVA. So these are the considerations of the selection so far as these factors are considered. So first is diversity factor, second is load factor, third is duration factor for altitude, next is duration factor for temperature. These four are main. Now the next is generator control. This generator control comprises these features. There is engine control inbuilt, then generator protection relays are there, then engine protections are there, and GCB operation they are there. So these are the all the parameters we read into this. This is all electronic equipment and measurements are done. Yeah, synchronizing. So whenever the demands are more and one single generator cannot cope up with all the demand, so that time we can select combination is 400 kVA, is 200 kVA. When the demand is less, this 200 kVA set can be shut off and only this demand can be catered. So in synchronizing, there are three factors. Voltage must be equal for the both sets. RPM should be equal for the both the sets, and phase sequence should be equal of the both the sets. So synchronizing is done in this fashion. Nowadays, the synchronizing relays, digital synchronizing relays are available. In earlier days, I had done the by three lamp method and etc. etc. So those methods have now gone. Now the new generation, they don't know about this three lamp method and etc. That was a very tricky and critical thing to synchronize the DG sets. Now another thing is that parallel operation with the grid. Here the demand is internal, so synchronizing is done to cater internal demand only. Now here it is parallel operation with the grid. This is only grid power, and I am having a DG set which is not running continuously, but investment is there. It is just lying idle. What should I do for that? The capacity is very high, and I use it only for as a standby purpose. So what I do, I run the DG set and I sell this power to grid. It is connected to the grid itself. So whatever extra time is available with me, or if there is excess fuel available is with me, so I utilize this for gaining this advantage, and I sell to the grid. So schematically, if you see here, uh, the grid power, it is being loaded on this side. Grid power is connected, and DG is running, and this energy, this power is fed to grid. So we get money from that. This was actually a self exercise. Okay, these are small formulae. Uh, they are available in our standard books only. But normally, what we do is just make a table to find out the total load demand. It is made in tabular form. Okay, DG set capacity should be, there are some thumb rules. DG set capacity should be 20% higher than the calculated demand. Yeah, one more thing. DG set can sustain two times its rated capacity for a short time, that is up to 3 seconds. That is momentary motor starting load. It means, suppose um, we are doing an exercise of say uh, weightlifting, something like that, and we have to just lift the load. Our normal capacity is say 20 kg lifting, but momentarily we can lift 40 kg, but for a 3 seconds we just show that yes, I can lift, which is my maximum power. So in that fashion, DG set can sustain two times the rated load. That is just a starting demand by the motor. Then alternator can withstand 20% phase imbalance in the current, not more than that. And power factor of the load should not be less than zero. 0.8. So these are the conditions for maximum load to be put on any alternator or DG set. Then the next criteria is a sequencing of the load. So what happens to DG characteristic? Here we consider first condition. So there are four loads in the factory. The first one is lighting load, conveyor is there, pump is there, compressor is there. These are their respective kW or and in terms of kVA also. So it is 20 kW. In lights, kW and kVA are same because their power factor is 1, the power factor is unity. No starter is needed for that. So as soon as the lights are switched on, the load on the generator will be 20 kVA only. Starting is 20 kVA. There is no separate kick on the generator. It is 20 kVA. So once the lights are started, 20 kVA load is continuously on. Next, the conveyor is started. The power of the conveyor is 5 kilowatt, and the starter for the conveyor is direct online. So whenever there is a DOL starter, the motor draws 6 times current during starting. And as a characteristic, the starting is normally up to 3 seconds, 4 seconds for pump applications. For mill applications and for larger loads, the acceleration time will be much higher. And that time selection of DG set is a very critical thing. We have to find out how much is the acceleration time. So here, what is mentioned in this statement, that short time 3 seconds. So 3 seconds is the acceleration time of the motor. If it is more than that, we have to go for higher rating. Say now, okay, come to conveyor. So initially 20 kVA load is running. During starting, 42 kVA was the kick. So 20 kVA initial working plus 42 kick. So kick on the load on the alternator was 62. Ultimately, after 3 seconds, this 27 kVA are standard. So 20 plus 27 will be the, again I will say, base load. It is running. Now after this I start the pump. Now the pump is having star delta starter. For star delta starter, the starting kVA or the kick is 3 times. So here for 12 kVA load multiplied by 3, so that will be 36 kVA starting. Initially 27 is working plus 37 kick, so kick goes to 63 kVA. So still I say this is the maximum kick. After this acceleration time is over, once it is settled down, this 12 is added to 27. So the steady load on the generator is 39 kVA. Now look what happens. Fourth, I start the compressor. The compressor is 60 kVA, and the compressor is motor is also having direct online starter. So it is going to take 6 times the demand during starting. So 60 into 6 is 360 kVA. Already 39 are working. 39 base plus 360 kick load. That kick load goes to 399 for 3 seconds, maybe 4 seconds, something like that. But after starting, after 3 seconds, the load is 99 total. This 39 plus 60 is 99 kVA steady load. So I have started lights, conveyors, pump, compressor. Now the entire load on the generator is 99 kVA. So should I go for 100 kVA or 125 kVA? If I consider 100 kVA is the load, yes, I consider this 100 kVA plus 20% extra. So it is say 118, 125 kVA is ideal. But what happens? We have to consider this kick load. The kick load is 399 and generator can sustain only 2 times the load. So if we consider 400 kVA is the kick demand, the generator should be of 200 kVA for just for to take the load of the starting of the compressor. Only for one load I have to go for 200 kVA, but the steady load is only 100. It means continuously I will be running the DG set at 50% load, which is not economical. Unnecessarily, I will be using wasting the fuel. What should I do? So instead of this motor starting at the last, what should I do? Say I take an advantage, पहले लाइट चालू करो बाद में कंप्रेसर चालू करके ले लो, विच इज हायर डिमांड जो है वो. So what is the change happened over here? Initially it was base was 20 plus the largest started was 360 kVA was the demand. So 20 plus 360 it is 380, and further the smaller loads are started. But again, this 380 divided by 2 is 190 kVA. I am not having any advantage of starting the compressor earlier. So I think something differently. So can I use the star delta starter instead of DOL? Is it feasible? So what happens? The starting kick is reduced to half. So instead of 360, it has come down to 180. What happened? Initially, the base load was 39 plus the kick is 180. So the kick load is 219. This is not going to change because ultimately all loads are same. We are here thinking for the kick demand. So 219 divided by 2 is 110 kVA. So yes, I am very much near to this my normal average load, 100 kVA and 110. Yes, this is absolutely okay, no problem. But I consider something still different. Now this star delta starter and compressor, can I start it at the second place? If it is okay, then the 180 will come at the earlier, and advantage is that instead of 219 kick load, my kick load is reduced, so thereby reducing the heat losses and etc etc. But again, this 99 kVA standard, say 100 kVA, 200 kVA, half of that is 100 kVA. So this is absolutely okay. But still, I say that for 100, if steady load is there, 125 kV is ideal. Now, yes, I am satisfied. Whoosh. Yes, my selection is correct. But for that, we have to consider compressor to be started at the second place with star delta starter and not with direct online. So these are the starting sequence and importance of using the starter. Nowadays, instead of star delta starter, we use soft starter. There, the starting demand is reduced to 1.5 times only, not 3 times. So the size of the DG set is still reduced, and we get the advantage over that. So this is the importance of starting. Now there are some other considerations. The effect of the unbalanced load. Uh, if the unbalance is higher than 20%, then there will be much more heating. I will not go very deep into this. Mm, yes. What happens in short? Effect of unbalanced load and low power factor is uneven heating of the winding. Uh, I will give you one example of unbalanced load. Suppose there are three workers, तीन मजदूर काम कर रहे हैं, एक कंस्ट्रक्शन साइट है, तो दे आर जस्ट प्लेसिंग द वेट, एंड द वेट्स आर नॉट इक्वल, देर आर अनइक्वल वेट उठाने का काम है. तो जब ज़्यादा लोड हो जाता है तो एक फेस पे लोड ज़्यादा आता है, so thereby the heating will be more. So uneven heating of the winding will be there, currents will be imbalanced, uneven torque or the power is generated in the windings, uneven speed of the motor may happen, higher current from the neutral current it passes, and heating of the earthing neutral point. And correspondingly, whoever is carrying all this current, say the same current is passing through the cable, to the switch gear, through the transformer. So all these equipment, those are in line with the motor, get affected and they are heated up. So the losses are increased everywhere, those who are conducting the current, because of the unbalanced and low power factor of the load side. So whenever we are doing energy audits, we must be very critical while seeing what is the power factor of the equipment. This is very important. Normally, it is overlooked. That may happen. Now, one more important thing is that neutral earthing. Earthing should be done properly. There should be uh, uh, okay. This earthing chapter I will take it at the last. They are given in the book. So far as other factors are considered, I will focus more on this load pattern. Yeah. Suppose uh, there are multiple loads. Uh, I think we will skip this one because in earlier example we have seen this. Yeah. While assessing or auditing the total energy audit or the basically load, this pattern has to be followed up from their logbook. So early for 24 hours, what is the load pattern? That is important. And from that, we can calculate how much is the utilization of the DG set, whether standby set is required, whether the only two sets are required, one for the night or one for the day. So for combination purpose, these patterns must be studied. This is one of the main and basic table we form at the beginning, or rather before the audit. We demand this information from the customers. Tell us the your load pattern. This for selection purpose we have already covered. So yeah, characteristic of the power factor. There are different characteristics of the load. Here the load is same, load remains same. But here, the load on donkey, load on horse, and load on elephant. Say it is 5 kW load, 5 kW load. If you see this one, the donkey is overloaded, whereas the speed of the horse and the load and the proportion is absolutely okay. There is no problem. But for this 5 kW load, 5 kW pump, we are using 25 HP motor, prime mover. So this is not economical. So the power factor of this system is less. So as an example, if the pump is 5 kW, the motor should be just higher by 10 to 15% than that. Should not be more than that. Otherwise, the power factor of the motor will be less, and unnecessarily we will be paying penalty on that, or the current losses will be very much larger. So this is we must adhere. Now the wasted recovery potential. Whenever there are multiple gensets are there, uh, waste heat is to be utilized. The best way to measure the waste heat or the locations or the potential is to use IR camera or the thermograph. uh, it can detect hotspot, not only hotspot, but it can detect the entire range around it. Also it gives the photo image. So this is the base instrument for thermal efficiency measurement and these characteristics. Here you see the photograph taken on this thermograph, this thermal analyzer. This is turbocharger. The turbocharger temperature is around 257 degrees. You see here the red color or the dark red color, brown color, which is nearer to this. And actually, on this chart, on the photograph, it is mentioned 257.4 is the maximum temperature over here, and further it is less. Now, so the hot air is inlet to the turbocharger, and from this the cold air is forced there. So on the permissible normal range is 500 to 700 degrees at the exhaust. So it is run on the exhaust temperature. Also, the exhaust can be measured. It is at the chimney end also. So whatever is the hot temperature at this, we can see it is 140 degrees. So we see that we have got a potential to utilize this energy. How much is the potential that can be easily monitored, easily measured instead of any calculations or logbook calculations. So this IR camera is very much useful. You see at the top, it is 178 degrees is the exhaust temperature. So whatever is the inlet at the turbocharger and what is the outlet at this chimney level. So from this we can just calculate what is the potential for a waste heat recovery. These are actually photographs I had taken when I had done the total audit at Hindustan Petroleum pumping station uh, in Rajasthan. I had done. So I have got some data from that. These are the photographs of that particular project. So this waste heat is recovered from these heat exchangers, and the calculations are given next to this. So the equipment, okay, the potential is like this. Whatever is the diesel engine is there, then this exhaust goes over here. From exhaust, heat exchangers are there. Then from the process, it goes to process tank. This is the recovery system at every place, from the radiator, from the oil cooler, etc. So this is one type of the heat exchanger. The smoke goes from this after turbocharger. The smoke goes from here, which is at 400 degrees, and it comes out as 60 degrees. So in between the cold or water is passed, hot water is taken for the process. So here is the calculation. This calculation is given in the book. We will just have the look over this. Quantity of heat output, temperature of exit gas, and time period. So these are the main factors given in this formula. So this figure is normally given kWh output per hour, 8 kg gas. It is also specified by the diesel engine manufacturer. I will show you that slide also. This is the specific calorific value of the flue gases, and this is the temperature range available. What is the turbocharger temperature? Minus 180 up. We can recover up to 180 because outlet air cannot be exactly at 30 degrees at 40 or ambient degrees. It cannot be there. So we have got a margin of this. The temperature of flue gas after turbocharger assumed to be higher than 180. If it is less than 180, the system is not economical. There is, because the heat available is very less, wastage is very less available. So here is the example. This is 800 kW. They have mentioned 8 kg gas per hour. Then this is 480 is the gas temperature minus 180. So this is the potential available. Example is given by 1100 kVA, load is 800 kilowatt, exhaust temperature is 480. This is the data given and the observations are there. Now what we have to look for is the optimization by the DG set. A list of the loads, make, find out what are the essential loads to be put on DG set, find the maximum load at any given point of time, calculate the demand, apply the derating factor, and find the potential for waste heat recovery. Then factors affecting performance at site conditions. At the ambient temperature, everybody gets exhausted. Even the diesel engine gets exhausted. So derating factor is applied. So at the cold condition, everybody is rather happy and comfortable. So this is the uh, chart for the correction factor for the temperature. Say at mean sea level and for the temperature, both the derating factors are there. At 1000 meters, say 0.95, uh, it is nearer to 1. But as the mean sea level goes increasing, the factor goes on decreasing. We will have to divide it by these factors. Similarly, for temperatures also. At 40 degrees ambient, there is no derating factor. 40 degrees, it is 1. Or as the temperature goes on increasing, we have to consider derating factor at a higher thing. So this table is also given in our book. This is a graphical presentation, same thing. Duration for the altitude, this happens at the higher altitude, oxygen is very less. At sea level, oxygen is very good, so no duration is required at mean sea level. This is a graph. In duration of the power factor, if the load is having good power factor, yes, our left efforts are less, so less fuel is required for better power factor. And if the power factor of the load is very less, if the load is sluggish, then the efforts are more, so we have to consume more fuel. Our alternator is not effective at that thing. So this is the duration power factor for the uh, uh, duration for the power factor of the load. Then critical and transient loading. Whenever there are any harmonics, again generator selection becomes critical. We have to consider the KVAs and etc. etc. So what are the critical loads are there? UPS, welding machine, X-ray machines, rectifiers, servo stabilizers. They make many times problem because the waveform is not sinusoidal. It should be like this, but the uh, CT scan machines, they create some type of waveforms. This was also from my exercises and some assignments. I got this. So in the CT scan, initially for very small time, very high power is required, and that time the AVRs fail and the generator fails, and the customers start complaining. So these are some of the waveforms. The waveforms are distorted because of the harmonic loads, because of the UPS loads. UPS are something like that. So there are 6 pulse UPS, 12 pulse UPS, 3 pulse UPS normal. So they create very much harmonics and imbalances in the system. Servo stabilizers also uh, critical load. Spot welding machines, they consume very high current. Say here it goes up to even 7,000 amperes like that for a very short time. So and these are some various waveforms. Transient switchings are there. Ultimately, for AVR, whether for machine or for the man, this part is very necessary. Whenever there is voltage dip in the system, it has to be recovered within this time. If the time period is exceeded, the AVR fails and generator is not able to develop the voltage. It is not able to recover the voltage. That's why it is called as a recovery time. This is a recovery time. This is a recovery level. So even for our ECG also the same form is there. We have to recover the pulse form. So we have to maintain for ourselves and for DG set the same thing. The neutral earthings are there. I will share some another things earlier we had seen that technical spec. Yes. Okay. Can you see this? Is it visible?
Yes, sir.
Yeah. Now here you will get most of the calculations and answers in this. This is a design data declared or selection data by Mahindra and Mahindra genset. It is 200 kVA genset. You look carefully. Uh, Basically, you look at the red cells, red background cells. These are important. Genset parameters, kW rating, kVA rating. For the alternator, it is 160 kW electrical, equivalent 200 kVA. So how it is 200 kVA? 160 kVA declare divided by zero point 0.8 power factor. The design of the alternator is for zero point 0.8 power factor load, not less than this. So 160 divided by zero point 0.8 is 200 kVA, simple way. Now this 160 kVA means root 3 multiplied by voltage multiplied by current 278 multiplied by power factor zero point 0.8. So this becomes 160 kVA, which is a rating, which is a rated capacity, that is declared capacities. Now come to next part, which is rated output. Now these are engine parameters, engine sheet. Rated output of the engine is 180 kW. Here you see electrical 160 kW, mechanical 180 kW. So it is 10% higher than alternator. Engine is larger by 11.1%. Now, next thing. This is standby output. Rated output is continuous. Standby output is for maximum 1 hour. For 1 hour, it can stretch up to 198 kW. Its rate continuous 180, 198. See what is the ratio? 180 divided by 198 is again 11.1%. It's a 10% by and large. So here there is a critical observation that for standby operation you should not go beyond 198 and for 1 hour only. Next parameter, uh, displacement 7.12. Okay, that is the size of the engine. Let us not see that. Alternator efficiency at 75% load. Normally, the alternators or engine or any equipment is run at around 80%. We never load 100%. Even though we are capable, we don't work at 100% capacity. Never. Our best efficiency is 80%. So similarly, whether engine or alternator, their best efficiency is normally they are at 75%. Nowadays, because of the increased technology, the efficiencies are almost constant from 75% load to 100% load, or say 95% load. After 95%, efficiency decreases. So alternator efficiency is 92%, and overall thermal efficiency of the engine is 40% only. So engine coupled to alternator, input to engine and output of alternator. The, if you multiply this, the overall efficiency of the DG set is 37% as per this calculation. Now see the other parameters for this mechanical efficiency, etc., etc. Let's forget that. Fuel system, we are not concerned about it right now. Fuel filter, air filter, etc. Lube oil system, capacities, blah blah blah. The manufacturer says give us most of them. Now here the cooling system is there. Yes, in cooling system it is water cooled engine. Type of cooling water cooled, radiator sizes, airflow, etc. Fan power, there is a fan required for the radiator. So fan consumes 8 kilowatt. 8 kilowatt is a fan loss. Now next, see what happens. Heat rejection details. It is given in the bold by the manufacturer itself. Heat rejection to coolant kilowatt. 90 kilowatt heat is wasted just for cooling, that is required for the radiator. Heat rejection to charged air cooler, it is 37.2. Heat rejection to exhaust is 146 kilowatt. And heat rejection from engine surface, it is 18.3. So by all put together, it is 291 kilowatt is the total heat loss. Now, here is there is the potential for heat recovery system. Now we calculate it below. This exhaust gas flow, this figure is given by the manufacturer. This is not any fictitious. It is 860 kgs per hour is the gas flow, exhaust gas flow. Now, what is the potential for heat recovery? Suppose this set is running for 24 hours a day and 860 kgs per hour is the gas flow, hot gas, and it is happening at 650 degrees. They have mentioned maximum exhaust temperature 650 degrees. So 650 degrees per hour multiplied by specific heat calories. So the calculations comes over here. 24 into 860 into 650 into 0.25, so and so. So considering this 3900 calories of per kWh, it is up to 162 kilowatt. That is the potential heat recovery we can get out from this. And now see the calculation at the bottom. Maximum output, it is 198 that we have seen. This is 198 kilowatt given by the manufacturer itself. This is the standby output, means it can run up to this. Then the losses, total losses, they have mentioned 291 kilowatt. This is as per the data itself. So what is the input? Input is nothing but the output plus losses. So 198 plus 291, so total input is 489 and output is 198. So output is 198 divided by 489 is 40%. Again, the same thing. So what the manufacturer says that the overall engine capacity thermal efficiency is 40%. It is established over here. We have seen in the earlier also that so far as the total efficiency is considered, it is 40%. So if somebody is saying that our engine efficiency is 60%, 65%, yes, don't believe. So these are the parameters and factors of the uh, diesel engine. Okay, so far as the earthings are considered, uh, I don't think. Normally, the earthings are given for the body and for the neutral also. There are two systems. The neutral should be grounded and the body also should be grounded separately. But nowadays, actually earthing is a very big and very deep chapter. So it is not directly concerned with energy conservation or like that. But yes, for the installation, for safety and for protection, this is very, very, very important subject. I do undertake assignments for this electrical safety also and for this installation and earthing also. That's a different chapter. Now, if you are having any questions, yes, we have got time of 10 to 15 minutes. Do you have any questions, or you can start your you can switch on your videos also. Yes, I have stopped sharing. You may switch on your videos and we can chat or you can ask questions also.
No questions from my side, sir.
Either no questions means have understood everything or nothing is understood.
Yeah, yeah, understood.
Uh, have I left anything from the book three? Uh, okay. Do you think that have I missed any point, any topic from the book? Chapter 9, book 3, chapter 9. Yes, Mr. Satyanarayan.
Yes, sir.
How's the session? Is it
Yes,
quite
sir.
elaborative or you need any explanations?
With turbocharger, how much power we can save, sir? With turbocharger.
Huh?
Turbocharger.
Huh?
By using turbocharger, how much power can be saved or can be increased?
We can get advantage up to 10% also. Up to 10%. Yes.
10%.
That is basically, it gives the overload capacity can be increased by that.
Or that is air quality also will get increased, no, sir. Air gets compressed and quantity also will be increased.
Yes, yes. Nowadays, if you see, the even for the automobiles also,
Sir.
whatever engines earlier were there for 1000 cc engines, now 900 cc engines with turbocharger are giving that much power.
That is okay.
Yeah.
So any question will come, sir, from this topic? In
Okay,
and so,
normal questions, mostly the questions will be on wastage recovery calculations
yes,
and some electrical load calculations and selection parameters. So questions will be on considering the diversity factor, load factor. These two things you just consider. They will give the total load. Say load is 250 kVA is the load, connected load is 300, and select the genset for that, or whether the selected genset is suitable for this factory. So this kind of questions will be there.
so gas DG set and then this diesel DG set. Which one is better, sir? Actually,
Pardon?
gas and gas DG set is there, sir.
Gas is always better because the pollution is less, the calorific value wise also we get the advantage, comparatively maintenance is less. So these are the advantages of gas over the diesel. But
Gas.
again, availability and these things, these are the factors. Availability, storage basically. Storage of the diesel is comparatively safer, I will say. For gas, your norms for the storage and handling is critical.
Certainly.
Yeah. Yes. Then shall we uh, shall we say off?
Yes, sir.
Yeah.
Thank you, sir. Thanks a lot.
Thank,
Okay. Bye
thank
bye. The next session, I think it will be started at 5:10 within 5 to 10 minutes.
you.
Next, Mr. Daspute sir will be there. I think so.
That's better.
Yes. Yeah. Okay. Bye bye.
Okay, sir. Thank
Yeah.
you.
I will just keep it on for the next session. Yes, I say now the recording is, I will be stopping the recording.